Welcome back to our channel. Today, we're diving deep into the world of cryptography to implement the Diffie-Hellman key exchange algorithm using Java. If you want to understand how secure keys are derived in a potentially insecure environment, then stick around. First, let's talk about what the Diffie-Hellman key exchange is and why it's important. The Diffie-Hellman method allows two parties to generate a shared secret over an insecure communication channel. This shared secret can then be used to encrypt messages between the parties. To start, we need to understand some mathematical concepts behind the Diffie-Hellman algorithm. At its core, it operates on the principles of modular arithmetic and prime numbers. We choose a prime number, p, and a base g. Both parties will use these values to generate their own public keys. Let's jump into the code. First, we'll set up our Java project. Create a new Java file named Diffie-Hellman.java. This file will contain the class that implements the key exchange. Next, let's implement the method for generating a private key. Each party needs to select a private key, which is a random number. For simplicity, we're going to simulate this process by using constant values, but you should use secure random number generation in real applications. Now we need to calculate the public key. The public key is calculated using the formula public key equals g caret private key mod p. Let's create a method that takes a private key as input and returns the public key. To wire things up, let's create the main method in our class to simulate two parties exchanging their public keys and deriving a shared secret. Let's print the public keys to the console to see what we've generated so far. Now, we need to compute the shared secret. Each party will use their private key and the other party's public key to compute the shared secret using the formula shared secret equals public key caret private key mod p. Let's implement the shared secret calculation in our main method. We'll compute the shared secrets for each party and print them. Now that we have our shared secrets, let's run the application to see the output. Here's what the output should look like. We will see the public keys generated for both parties, as well as the shared secrets that both parties derived. As we can see, the output demonstrates that both parties, using their respective keys and calculations, produced identical shared secrets. This is a crucial property of the Diffie-Hellman key exchange. Now, in practice, the private keys should be randomly generated, and you should ensure that they remain secret. Let's enhance our program to use Java's secure random class for generating a secure private key. We also want to ensure that our prime number and base are actually prime. In a real implementation, you'll want to verify these values against a list of trusted prime numbers. We will keep them simple for demonstration purposes. Before we finish up, let's add a few more features to our implementation. First, we can encapsulate the actual Diffie-Hellman process in a separate method that can be reused. This way, we can compute shared secrets for any two users. Finally, integrate this method into the main method, so whenever we run the program, it performs the Diffie-Hellman exchange. Now, you should have a complete implementation of the Diffie-Hellman key exchange in Java, including secure random key generation. Remember, in real-world applications, you also need to consider security against replay attacks and further encrypt the shared secret before using it. As a reminder, be cautious when dealing with cryptography. Always stay updated with best practices in the field. That's it for today's tutorial on Diffie-Hellman key exchange. If you found this tutorial helpful, please give it a thumbs up, and don't forget to subscribe for more programming tutorials. If you have any questions, leave them in the comments below. See you next time.